Hilltop Event is a suite of event analysis processes. Event considers the probabilities of maxima and minima and is used for risk analysis. Event is used in the design of stop banks and in the allocation of water resources. Other Hilltop processes read data for a measurement and calculate statistics based on all the data you've asked Hilltop to look at. In event processes, you must first select samples of the data that represent the events you are trying to analyze. How many samples you select and the way you select them is very important. Your sample set is an attempt to represent all the events that have occurred, including ones that have not been measured, and ones that will occur in the future. Consider a political survey done to gauge public opinion. The researcher asks a small number of people their views on the assumption that the sample represents the total population. In event processes, monthly extrema are calculated first, then the extrema are placed in partitions, from which one sample is generated per partition. Partitions ensure that samples being analysed are independent of each other. For example, the data may include a set of storms that produces samples across 3 months in a particularly bad winter, but all the storms are part of a single meteorological event. Setting the partition to 1 month will produce 3 samples in the set, and they could bias the analysis. A partition of 3 months will give 1 sample that represents the whole season, and the statistical analysis is now focusing on comparing one winter with another. That said, the partition is most often set to 12 months, especially if you have 20 years or more of data. This partition ensures your samples will be independent of each other. Like with all event analyses, there is an assumption conditions are stationary, that is, the climate remains the same. Now, ultimately all natural systems are non-stationary, but because change usually occurs slowly over a relatively long period of time, as long as your analysis covers a relatively short period of time, the change is so small that it doesn't warrant complex analysis. We need to take a considered approach to climate change and ultimately need to work with the tools we have available. Do be aware of the interdecadal Pacific oscillation when setting your time range. Major temperature and rainfall fluctuations in New Zealand coincide with the positive and negative phases of the interdecadal Pacific oscillation. Reversals occurred around 1945, 1978 and 2000. Be aware of the possibility of non-stationary conditions or analyze data between changes or symmetrically across a change to avoid this. You should only ever consider a return period of no more than around 2.2 times the length of the record you have. To avoid seasonal variation, you should also analyze like seasons or year-on-year data. Now, having a set of samples is all well and good, but essentially it is still just a bunch of numbers, and we want to apply some meaning to them. Remember bell curves from high school maths? You would have looked at people's heights maybe, or the size of things produced by machines, grouped them into classes, and graphed the number of things in each class. Your histogram would have been symmetrical around the mean, and you discovered that this was called a normal distribution. From there, you learnt about the probability density function, and by finding the mean and standard deviation, you could then work out the probability of things being in a particular range. In hydrology, there are a number of different distributions, and the art is choosing which best fits your data. The L moments process helps here. There is also an issue of how you calculate the parameters in the distribution, and that's where the fit distribution process comes in. It will calculate the relevant parameters, and you can see how well your chosen distribution fits your data. All of the event processes will give you a result, but what you get out is only as good as what you put in.